Aldol condensations are extremely important reactions in organic chemistry, and let's look at first an aldol addition, where if we take something like acetaldehyde and add some sodium hydroxide, we form this aldol product, right? So the term aldol comes from the fact that we have an aldehyde here, and then the OL because we have an alcohol as well. Let's look at the mechanism for the formation of this. So if we start with our acetaldehydes, I'm going to go ahead and draw it out here, and we look for our alpha carbon, right? It's the one right next to our carbonyl. So here is our alpha carbon. There are 3 alpha protons on that alpha carbon. I'm just going to show one here. And then we're going to have sodium hydroxide come along act as a base. So we have the hydroxide anion, so -1 formal charge on the oxygen. It's going to take this proton, right, leaving these electrons behind on our alpha carbon. So let's go ahead and show the carb anion that would result. Right, so we have our carbonyl, and then we have our hydrogen on the right side. And on the left side, we have a lone pair of electrons on this carbon, so we have a carb anion. So the electrons in magenta here moved off onto this carbon. We can draw a resonance structure, right? These electrons move into here. These electrons go off onto our oxygen, and we would form the oxyanion, right? So we have a double bond here, and then our oxygen up here would have 3 lone pairs of electrons, so -1 formal charge, and then a hydrogen. So the electrons in magenta moved in here to form our double bond. And so we know that the negative charge is best supported on an oxygen, so the oxyanion is probably the best way to show an enolate anion. However, for the aldol condensations, I'm always going to use the carb anion as our enolate anion. It's actually a little bit easier for students to look at the mechanism that way. So we're going to start with our carb anion. So I'm just going to redraw it down here. So here's our carb anion. Right, and once you form your enolate anion can act as a nucleophile, right? Because this carbon here is negatively charged. And because we use something like sodium hydroxide is not basic enough to completely form enolate anions. So only a small amount of your enolate anion is formed. And so this can act as a nucleophile and attack another molecule of acetaldehyde. So I'm going to go ahead and draw in another molecule of acetaldehyde. And I'm going to draw it in a particular way. I'm going to leave off the hydrogen, and I'm going to put it right next to this. It just helps me when I'm doing an aldol reaction here. All right, so if I know the carbonyl of my other molecule of acetaldehyde is polarized, right? The oxygen is partially negative, and the carbonyl carbon here is partially positive. So the carbonyl carbon is electrophilic. It wants electrons, and it's going to get electrons from our nucleophilic enolate anion. So these electrons here are going to attack our carbon, right? Push these electrons off onto our oxygen. So let's go ahead and show the result of that. So on the left side, right, we would have our oxygen with 3 lone pairs of electrons, and then we form a carbon-carbon bond here. So that's extremely important. And then we also have over here on the right our aldehydes. So let's show the movement of electrons, right? So these electrons right here, right? This is our carb anion. Attack our carbonyl carbon, form this bond, right? A carbon-carbon bond forming reaction to form an alk oxide intermediate. And so we could protonate our alk oxide with water, right? So water is right here. So we could show a lone pair of electrons picking up this proton, and we can go ahead and draw our aldol product now. So we draw our aldol right here like that. So the formation of a carbon-carbon bond makes an aldol addition, and then next an aldol condensation, a very important reaction in organic chemistry here. So there's our aldol product. All right, let's look at an aldol condensation, which is kind of a continuation of what we were just talking about, and you can form different products depending on reaction conditions. So for example, here we're starting off with acetaldehyde again and sodium hydroxide and water, but we're adding heat, so we're changing the reaction conditions, and so we're going to get a different product, and so we call this an aldol condensation. So you can see the product that we get is an enal. Right, so we get an enal, we get a double bond here for the ene, and then we have an aldehyde. Right, so you also hear it referred to as alpha beta unsaturated because this carbon right here is the alpha carbon, and this carbon is the beta carbon, and it's unsaturated because we formed a double bond here. So this is an aldol condensation. And to form this enal product, we're going to start with the aldol that we just made in the previous reaction. So acetaldehyde, right, with sodium hydroxide can form an aldol as we just saw. So let's go ahead and draw in the aldol product. All right, so the same mechanism that we just discussed. And I should point out that we're doing a base catalyzed aldol condensations here. So we have a hydrogen here, and then our aldol had an oxygen, and then a hydrogen right here. So there's our aldol. And if we look at our aldol, right, the carbon right next to the carbonyl is our alpha carbon, and there's still 2 acidic protons on that alpha carbon. So I'm just going to draw 1 in there. And then we can think about sodium hydroxide acting as a base and forming another enolate anion. So I'm going to have sodium hydroxide come along, so OH minus. It's going to function as a base, right? It's going to take this proton, right, leave these electrons behind on this carbon. So let's go ahead and draw that, right? So we would have our oxygen right here with 2 lone pairs of electrons, right? We would have our carbon now with lone pair of electrons making a carb anion, and then we have our carbonyl over here like that. All right, so let's once again show those electrons. These electrons right in here, right, forming our carb anion. And then to form our enal product, we can just think about, let me go ahead and draw an arrow here. We can just think about these electrons moving in here to form a double bond and kicking these electrons off onto the oxygen to form hydroxide as a leaving group. Right? So we can say that hydroxide leaves, and then we form our double bond. So I can go ahead and show that, you know, let's say these electrons right here were the magenta ones to form our enal product. And so once again, I'm using the carb anion form of our resonance structure instead of the oxy anion. So again, it's probably more appropriate to use the oxy anion, but it's just easier from a student perspective to use a carb anion to go ahead and form your enal product that way. So in terms of another product, right, this is the major product that we would form here, right? This is the trans product. So if we think about this double bond, these hydrogens are on opposite sides. So this is the trans product. So that's the major one. You would form a small amount of the cis product as well. So let me go ahead and draw that in. But the cis product would be the minor product because it has more steric hindrance than the trans product. So this is the major product, and I'm sure the one that your professor wants you to put on an exam question. So the trans product has decreased steric hindrance. All right, let's do one more of these aldol condensations. And so here I've drawn out the reaction, and so the question would be like, write a mechanism, write a plausible mechanism for the formation of this enone, right? So we have an enone this time. We're starting with a ketone, and so we have a double bond and then a ketone, so an enone product. So we're going to use sodium hydroxide, and we're going to heat things up here. So let's think about what would happen, right? So we have our ketone, and we have 2 alpha carbons, which are symmetrical, so it doesn't really matter which one we take a proton from. So I'm just going to say take a proton from this one. All right, so we take a proton from here to form our enolate anion, and once again I'm going to form the carb anion just to make things simpler. So we have our carb anion now, and then we have another molecule of cyclohexanone is going to come along. So let me go ahead and draw that in. All right, and we know we have a polarized carbonyl situation, partial negative, partial positive. So our nucleophilic enolate anion is going to attack right here, right? So we can show these electrons attacking right here, pushing those electrons off onto your oxygen. So I'm just going a little bit fast through this mechanism here, and so we have now a bond that formed, right? And now this oxygen right here is going to have 3 lone pairs of electrons around it, -1 formal charge, and I can go ahead and draw in the rest of my ring like that. So let's follow some of those electrons here. So I'll make these electrons in blue this time, forming the all-important carbon-carbon bonds right here, right? And then these electrons came off onto our oxygen, forming our alk oxide. Right, so we could think about water, right, protonating our alk oxide intermediate. So lone pair takes that proton, leaves those electrons behind, and hopefully we have enough room to draw the aldol. Right, so over here we would have our aldol intermediate. Right, we have our OH, we have our ring like that. Okay, thinking about what happens next, right? The carbon next to the carbonyl is the alpha carbon. So that's our alpha carbon, and so there's still a proton on that alpha carbon. And I don't really have a lot of room here, but let me see if I can draw in an alpha proton like that. And so we could have hydroxide once again functioning as a base, right? So picking up this proton, right, and then leaving these electrons behind on that carbon in red. So let's get some more room here. So now what we would have is our ring, right? We have our our carbonyl there, and then we have a lone pair of electrons on this carbon at -1 formal charge. Over here we have our OH, like that, and then we have our ring. Okay, so in the next step, once again, I'm not drawing an oxyanion, so I'm not going to draw the oxyanion form of this enolate anion here, but we could show these electrons moving into here, right, and pushing these electrons off onto the oxygen. And so let's go ahead and draw our product once we do all of that. So we would have our ring, right, we would have our carbonyl here, and then we would form a double bond, and then now we can see that we have our product. So let's follow those electrons. So electrons in blue here, right, these electrons move in here to form our double bond. Right, and then let's use red to show these electrons in here coming off, and so we get hydroxide as our leaving group, and we form our conjugated enone as our product. And so this is one way to represent the mechanism. And once again, the reaction conditions will determine what kind of product you get. Our enone here is conjugated, right? We have an alternating single-double bond situation, and so that favors this product here. So that shifts the equilibrium once again to make more of your enone. So practice doing a lot of these aldol condensations.